In this video, we're going to take a look at section 3.1, which is on solving system of equations by graphing. So before we get started on that particular topic, let's just introduce the concept as a whole. A system of equations is a set of two or more equations, all of which must be satisfied at the same time. So there's no special notation that goes along with this. They just give you a problem. In that problem, there are two equations listed, and the assumption is we're trying to find ordered pairs that satisfy all these equations at the same time. Any ordered pair that does that is called a solution to the system. So a solution to a system of equations in two variables is any x comma y that is a solution to each and every equation in the system. And that's what we're going to be looking for in these next few sections. We're going to talk about different ways of doing that. In this section, we're going to be looking at how to find a solution to a system of equations by graphing. But there are some other methods that we're going to learn later in the chapter. So in section 3.2, we will learn how to solve a system of equations by the substitution method. And in 3.3, we will learn how to solve a system of equations by the elimination method. So we're going to be seeing the same kind of problem over and over in these next few sections, but we're going to be talking about different methods that we could use to solve them. And it's good to know multiple methods because certain methods work best in certain situations. So it's good to have a good toolbox for dealing with these kind of problems. All right. So to solve a system of equations by graphing, what we're going to do is graph both equations on the same Cartesian coordinate system and then look for where they intersect one another. So the solutions to a system of equations are found where the corresponding graphs of those equations all intersect one another. So if we have two equations, we're going to look for where those two lines or where those two graphs cross one another. Every point where they cross is a solution to the system of equations that we're working with. All right, so let's apply that concept to this problem here. So solve the system of equations by graphing, then classify the system. And we'll talk about how to classify it in just a minute, but let's get the solution first. All right, so we have these two equations here. I'm going to write them a little bit further down on the screen. So we have x plus y equals 9, and we have x minus y equals 7. And we want to graph both of these equations on the same Cartesian coordinate system. Now these are linear equations, just like we were doing back in chapter 2. And we have a few different methods for graphing lines. We can use the slope and the y-intercept, which we could pretty easily do here, but I think there's a slightly easier method, which is to use the x and y-intercepts. And so I'll find the x-intercept by plugging in 0 for y and then solving for x. All right, so to find the x-intercept, we'll plug in 0 for y. That's the first step. So we'll have x plus 0 equals 9, and then we solve for x, and that gives me x is equal to 9. So I hope I said, I don't know, I was just thinking about what I said a moment ago. Hopefully I didn't say it wrong. So to find the x-intercept, you plug in 0 for y, and then you solve for x, and we get x is equal to 9 this time. So we get the point 9 comma 0. That's 1 point, but we need 2 points to graph a line. So we also need to find the y-intercept. To find the y-intercept, you plug in 0 for x, and then you solve for y. And so you can see why I chose this method for graphing, because finding the x and y intercepts from an equation of this form is pretty easy to do. It's easier than doing the slope, in my opinion. Because when you plug in 0 for x, that term just goes away and you get y equals 9. You really could do this without even writing very much down, right? We can kind of see what's going to happen. You plug in 0 for x, you get y is equal to 9. So we get the point 0 comma 9. And vice versa, right? To find the x-intercept, I plug in 0 for y. That goes away. I just get x is equal to 9. So I get these 2 points, which I will graph on the Cartesian coordinate system. So we have 9 comma 0, which is way down here on the x-axis. And we have 0 comma 9, which is way up here on the y-axis. And then I connect those 2 points with a straight line. So let me see if I can do that. All right, so let's start from this point here. Go right through here. It's a little bit, doesn't give me a lot of wiggle room here. I mean, how do I want to say it? Doesn't have I don't have very much control. It's kind of either in one spot or another. Well, now it does it, but for some reason right here it doesn't want to do that. So I'm going to leave it right there. It's a little bit off the mark, but hopefully not so much that we won't be able to figure out the answer. Because the important thing about this technique of graphing is that the graphs have to be precise in order to get the correct answer. So hopefully that's precise enough. So I did the first equation. So I'd like you guys to do the second equation, and we'll graph this one. I don't know, we'll do green, I guess. So let's graph this equation. So you'll pause the video, find the x and y intercept for this equation, right? So we did this one already right here. So find the x-intercept and the y-intercept, and then use that information to graph the line as well. So go ahead and pause the video, resume it. I'm not going to actually work out the details of it because I'm kind of out of space as it is, but I'll write the answers on the screen. All right. So what you should have come up with is for the x-intercept, you'll plug in 0 for y, so that term goes away, and you just get x is equal to 7. So you should get 7 comma 0 for the x-intercept. For the y-intercept, you're going to plug in 0 for x. This one's a little bit more complicated. You plug in 0 for x, and you get negative y is equal to 7. So you have to divide by -1 on both sides, and you get y is -7. And that'll be your y-intercept, 0 comma -7. We'll plot these points over here. We'll have 7 comma 0, and we'll have 0 comma -7, which is -7 on the y-axis. And then we will graph this as a straight line. So I'll start from this point here and try to go through this point and see if it gives me some room to work there. And so that's, yeah, so I don't know why I keep saying room to work. I don't know if it'll let me precisely mark the spot that I need to mark, but it looks like it's pretty close again. And I think we can kind of get an idea of where these lines are supposed to be intersecting. It's a little bit off the mark, but it's right here. And so I'm going to assume, let me switch back to this. I'm going to assume that the point where they're crossing here is at 8 comma 1. All right, so the answers should work out fairly nice. They're not going to give you a graphing problem where the answers are fractions or anything. So let me write that 8 again. So we're going to have 8 comma 1. So try to find the point. If it's really close to a nice point, you probably should just go ahead and use the nice point and not assume, you know, because really it kind of looks like it's at 8.1 or something like that. But I'm assuming it's going to be at 8 comma 1. And we can check to see if our assumption is correct, because this point, if it is the solution, should satisfy both of these equations. So we could plug that point into both the equations to make sure it works. So if I plug in 8 for x and 1 for y, I get 8 plus 1 here, which is 9. And if I plug in 8 for x and 1 for y here, I get 8 minus 1, which is 7. So that is indeed the solution to this system of equations. So the solution is 8 comma 1. It's where the two lines cross each other. Okay, so now it wants me to classify the system. So there are two categories on which we will classify the system of equations. All right. So we'll either classify them as independent or dependent, and the way you determine which term is correct for your system of equations is based on how many solutions you're getting. So if you do not get an infinite number of solutions, then the system is considered to be independent. If you do get an infinite number of solutions, then the solution is called dependent. So these two terms, the difference between them is it infinite or not infinite? If you have an infinite number of solutions, then it's dependent, but if it's not infinite, you call it independent. All right, and so in this example, the one we just did, we got one solution, which is not infinite, right? This is not infinite. It's just one solution. And so the classification for this system would be independent in regards to those two terms, right? So this is an independent system of equations. And then we have another set of terms that we have to decide between. Is this system consistent or inconsistent? And again, the way you determine that is to look at the solutions. If there are no solutions to the system of equations, it's inconsistent. If there are no solutions. If it has any solutions at all, whether it's just one solution or 5 solutions or infinite solutions, it's consistent. So in this case, it's solutions versus no solution. So going back to our last example, we have one solution, so we did have a solution, so it is consistent. It's only inconsistent if there are no solutions. All right, so how do I want to say this? We have a solution here, and so it is consistent. All right, so for independent versus dependent, you want to see, is it infinite or non-infinite? For consistent versus inconsistent, you want to see if there are solutions or if there are no solutions at all. All right. So that's how we will classify these. And unfortunately, they'll keep asking us over and over to do the classification. But by the end of it, we'll have a lot of good practice with it. So hopefully we will get it right on the test. Okay, solve the system of functions by graphing, then classify the system. All right. Now, here they're using function notation, and they're using different letters here, like F and G. And that's how function notation is supposed to be used. But again, they try to find as many opportunities to use the function notation as possible. It's really not that helpful here. So I'm just going to switch back to calling these just the y variable. So we have y is equal to negative 1/8 x plus 9. And we have y equals 5/8 x plus 3. All right. So if you don't like the function notation, just switch them out for the y variable again. And I really recommend doing that for this problem because the function notation in no way makes this problem any easier. So we'll just use y variable instead. Now for this one, we want to graph both of these on the same Cartesian coordinate system. But this time I'm not going to do x and y intercepts like the last problem. I'm going to do the slope and the y intercept because these equations are set up for that to work a little bit better. They're already set up in the slope-intercept form, so I can easily get the slope and the y-intercept from the equation. So the slope here is negative 1/8. The y-intercept is at 0,9, and I can use that information to graph my line. This is something, again, that we learned in Chapter 2, the previous chapter. So I'm going to start with 0,9, which is right here on the y-axis. And then the slope gives me a set of directions for finding another point on the line. And so I'm going to follow the slope as a set of directions. The top number is the rise, so it's going to tell me how far up or down to go. And I'm going to go down 1 because I'm going to think of that as a -1 there. So we're going to go down 1. The bottom number is the run. It tells me how far left or right to go. Because it's a +8, we're going to go to the right by 8. So starting from this point, we will go down 1 to the right 8. So this is going to be kind of hard for me to measure out here. I think right here is where we want to be. All right, so it's going down 1 to the right 8. We get another point right there. And then with those 2 points, we can draw our line. All right, we connect those 2 points with a straight line. Use a different color. And we'll see if it lets me do a decent line this time. All right, okay, this one's working a lot better than the last one did. Okay, have a lot more control there over how that looked. All right. And this one goes this way. All right. And we'll try to keep it as straight as we can. Okay, so that's our first line. So again, pause the video for the second equation and find the slope and the y-intercept. I'm kind of pointing it out to you. I shouldn't be doing that. Find the slope and the y-intercept and then see if you can graph the second equation and then resume the video to see if you came up with the right graph. All right. So what you should be finding is that the slope is 5/8, right? It's the number in front of x. The y-intercept is 0,3. So you're going to start from 0,3, which is right here. And the slope tells me to go up 5, right? It's a +5, and to the right 8. So I'm going to follow that set of directions, starting from here. Up 5 gets me to 8, and then to the right 8 gets me back to 8 again. 8 on the x-axis anyways. And so it's going to be this point. And I find that they will do this quite frequently where you use the slope and the slope for both equations takes you to the same exact point. So it makes it really obvious what the solution to the system of equations is. All right, so let's graph this as a line, right? So we have 2 points now, so we want to connect those 2 points with a straight line. And it would go this way, even though that way it's not really important to us for this problem. And so where they cross each other is the point that they share in common that we found when we did the slope, which is this point here, which is at 8, 8. Oh, sorry about that. 8, comma 8. Okay. And so that should be the solution to our system of equations. Again, it's not a bad idea to check by plugging it back into the equations to make sure it works in both of them. I'm going to assume that it works out just fine. To classify the system, it's just like the last example. We got one solution that's not infinite, so it's going to be an independent system since it's not infinite. And because we did get a solution, it's consistent. It would only be inconsistent if we got no solution at all. All right, so again, the same classification. It's independent and consistent. All right, let's take a look at this example. So this one, they're kind of nice here because it's multiple choice. So we just have to figure out which of these graphs seems to match up to these two equations without having to completely do the full graphing on our own. And then we want to classify the system of equations again once we figure out which graph is correct. So let's take a look at this first equation. We have 3x minus 9y equals 54. So because it's in standard form, I think the easiest way to graph this would be x and y intercepts again. So let's look at the x-intercept. We will plug in 0 for y, so I'll get 3x minus 9 times 0 equals 54. That gives me 3x equals 54. I divide by 3 on both sides. And unfortunately this time, we get x is equal to 18, which doesn't actually fit in the window of the graph. So this point is not one that we're actually going to get to see in any of these choices here. But it's at 18, 0. Let's see if the y-intercept is more helpful. We'll plug in 0. So this, I guess I should number these steps. It's step 1, step 2. Step 1 here is to plug in 0 for x. So we'll get 3 times x minus 9y equals 54. We get negative 9y equals 54. So this is step 2. Solve it for y. Divide by negative 9 on both sides. We get y is equal to negative 6. So we get 0, negative 6 as the second point for this equation. So looking through our choices here, any of these graphs that does not have at least one line at the point 0, negative 6, I kind of said that wrong. Any choice over here that does not have at least one line with the point 0, negative 6 on it can be eliminated. So for example, C, right? 0, negative 6 would be right here. Neither of these lines passes through that point, and so C cannot be the correct representation of the graphs. This one does have a point at 0, negative 6, so this one's still in contention. This one does not have a point at 0, negative 6, so B cannot be correct. This one also has a point at 0, negative 6, so that one is also still in contention. So it's either going to be A or D, and if you look for either of these, that bottom line is the same on both of them. So the only difference here is that for A, you get the same graph twice. So when I go to graph the second one, if it turns out to have the same exact x-intercepts and y-intercepts as the first one, then it's going to be option A, because option A is saying the two equations just give you this one line. Option B is saying you get two different lines here, but they are parallel to each other, and that's going to have some significance as well. So let's see what's going on with that second equation. So let me make some room here. Sorry, I kind of drew that funny. So let's look at the second equation. We have 2x minus 6y equals negative 4. So let's do the x-intercept first again, like we did in the last equation. We will have the first step, you set y equal to 0, so you have 2x minus 6 times 0 equals negative 4. That gives me 2x is equal to negative 4. You divide by 2 on both sides, you get x is equal to negative 2. That's different than x equals 18, right? So these do not have the same x-intercepts, which means it can't be the same line twice, which means A isn't possible either, right? So this line, this equation, has the point negative 2, 0, which looks like it's right here, right? Negative 2, 0. So it looks like D is the correct choice here. And so I'm not going to bother finding the y-intercept because I've already figured out which graph is correct. Now that I know this is the correct graph that represents these two equations, I want to find the solution to my system of equations, which is going to ask you next. So first it asks you pick the right graph. The next thing it'll ask you is what's the solution? And remember, for graphing, the solution is where the two lines cross. It's where the two lines intersect. But we can clearly see from looking at this graph that these two lines are not going to intersect. They are parallel to each other. And so if they never intersect, if they're parallel, then there's no solution to the system of equations. So when you're given the choice of what's the solution to the system of equations, you will want to choose no solution. That should be one of your options on Math Excel. Right? So it'll say option A, the solution is blank, and you type in the point that's the solution. Option B, there is no solution. Option C would be there's an infinite number of solutions. You want to pick no solution this time. All right. Because the lines are parallel. So keep that in mind. If the lines are parallel, the system has no solutions. If the graphs do not intersect, the system has no solution. Now, to classify this system of equations, first we want to decide, is it dependent or independent? And remember, the difference there is whether it's infinite or not. If it's infinite, if there's an infinite number of solutions, then it's dependent. But this doesn't have an infinite number of solutions. It has none at all. So it can't be dependent. It's independent. Which I know is kind of weird because there's no solution here, but it's always independent unless there's an infinite number of solutions. Then it becomes dependent. So it's independent. Now, is it consistent or inconsistent? The difference there is whether it has any solutions at all or no solution. This time we actually have no solution, and that's the only time you would ever select inconsistent as your classification. It's inconsistent because there are no solutions. That's the only time you pick inconsistent. If there are any solutions at all, it's consistent. All right. So in this case, it's independent but inconsistent. All right. So let's take a look at one more example. This is the last one for the section, so it's kind of a short section. Same thing as the last one. We have two equations. We're trying to find the graphs for them, but they're giving it to us as a multiple choice option. So we just have to get just enough information to know which of these multiple choice options is correct. And then based on the graph that we pick, we'll decide what the solution is. And then from there, we can classify the system of equations. So we will start with the first equation, 9x minus 5y equals 15. Okay, so again, it's in standard form, so I would recommend doing x and y intercepts. And I know I normally start with the x-intercept, but just looking ahead, I'm going to plug in 0 for y, and then I'm going to get 9x equals 15. And that doesn't work out to be such a nice answer. And I might not really need to know the x-intercept. I just need just enough information to figure out which graph over here is correct, to eliminate 3 of them and leave just the one that's correct. So I think I'm just going to look at the y-intercept for this one for now. If I need the x-intercept, I'll come back to it. Let's just do the y-intercept. So step 1, we have 9 times 0 minus 5y equals 15. That's plugging in 0 for x. And then step 2, solve for y. So we divide -5 on both sides. We get y is equal to -3. It works out to be a nice answer. So we get 0, -3. So any graphs over here that do not have a line containing the point 0, -3 can be eliminated. Now look, these numbers are going by 2's here, but looking at this one, it doesn't look like it passes through the y-axis at -3. It looks like it's a little bit higher than that. So A doesn't have any graphs that contain the point 0, -3. B does, right? There's one right here. It looks like B, like this line right here is passing through 0, -3. C also does. It has a line here passing through 0, -3. And D does as well. All right, so we eliminated one. That's not the greatest. Before I go back to find the x-intercept for this, let's consider the other equation. Maybe that'll help us eliminate things a little bit further. All right, so we have 5y minus 9x equals -15. Let's just do the y-intercept here again. Step 1, plug in 0 for x, so we'll have 5y minus 9 times 0 equals -15. And then we'll solve for y, so we're going to get 5y equals -15. So again, this is a 0 right here. I'm sorry, it's hard to read, but that just goes away. And then we divide by 5 on both sides, and we get y is also equal to -3. Well, that's interesting. We get the same y-intercept. Now you might think, well, this doesn't help us eliminate any further things because it's the same point again. So how can we eliminate more choices if we're getting the same point twice? But it does, because this tells me that both equations have to have the y-intercept at 0, -3. Both of my lines have to be crossing through this point. So B cannot be correct because the second equation here does not have the same y-intercept. It has a different y-intercept, so B can't be right. They have to both have a y-intercept at 0, negative 3. D also cannot be correct because they don't both have the same y-intercept. So the only option left is option C, which is telling me that I'm really getting the same line twice. If I were to graph both of these on the same Cartesian coordinate system, they would line up exactly the same as one another. You get the same line twice, which means they intersect everywhere together, right? The two equations intersect at every point. They share every point in common, which means every point on this line is a solution to the system of equations. So whenever you get just one line out of your two equations, you have an infinite number of solutions. And I think you'll have an option on Math Excel that lets you select that. So again, one option is option A, the solution is blank. Option B, there's no solution at all. Option C, there's an infinite number of solutions. Now there's more you could say about it than just it's infinite, but I don't think Math Excel asks you to do that in this course. So we're just going to say there's an infinite number of solutions, right? And that'll be the choice that you pick. Now to classify this, our first classification, is it independent or dependent? This is the one situation where we would say it's dependent. There's an infinite number of solutions, and that's the only time you would ever pick dependent as your classification. Otherwise, it's independent every time. And then for consistent versus inconsistent, you only pick inconsistent if there's no solution. Well, we have the opposite problem here. We have an infinite number of solutions, so we do not want to pick inconsistent. That only applies if there's no solution at all. So this is still consistent. Right? If there's any solutions, it's always going to be, sorry, I almost said the wrong thing. If there's any solutions, it's always going to be consistent. The only time it's not consistent is if there is no solution. All right, so that concludes section 3.1 on solving systems of equations by graphing.